We ended talking about the cyclic or the tricyclic kind of intermediates, and we looked at our diazomethane. Okay, and that if we draw out a Lewis structure, that's what's really drawing our attention to the reactivity of this guy. That carbon is both a positive charge because it has a great leaving group, and it has a pair of electrons. So that carbon can act as both a nucleophile and an electrophile. It satisfies the conditions for our cyclic or our tricyclic structures. Okay? If we move on to this guy, okay, what do you see in the reactivity in that structure? Do we have electrons?
Yes.
Yes. Okay, so it does satisfy at least that aspect for our cyclic tri. Okay, let's take a look at that top oxygen, now with the red lone pair. Okay, does it have a weak bond connected to it?
No.
I would say yes, it does, but does that weak bond break away from the oxygen atom? No. Okay, that bond is weak, but it's not going to break away from the oxygen. If anything, it's going to go the other direction towards the oxygen, which means that atom can't act as an electrophile.
But
Listing. Because what we're talking about doing is the pi bond coming in and attacking the oxygen. Okay? If it does that, we have to have that weak bond to break out. Okay? That's not a good bond to break that pi system in that direction because you're shuttling electrons.
If you have a good leaving group, if you're trying to do an addition and you're trying to verify that that's a good leaving group, that's a double bond. So that's a pretty strong overall.
And remember, double bonds are irrelevant. A leaving group just takes the electrons. That does not mean it leaves the structure.
Oh.
It means the electrons left the atom.
Okay.
Okay? In the classic definition that we've seen for our leaving groups and substitutions, it's left the structure. It doesn't necessarily have to. Your leaving group just has to take the electrons.
So you had that without the arcane and that carbon, and that was like a negative carbon, then you would have a good leaving group?
So, again, if we look at that bond, should that bond, that pi bond, break where the carbon takes the electrons? No.
But what I'm saying is if it were going the other way and the carbon was negative?
So if the carbon had electrons, yes.
And then it would be a good
Yes.
leaving group.
Okay, this is going to be a horrible drawing because it exceeds the octet. So just to kind of ignore that. But if that carbon, for whatever, had those electrons, okay, then what can happen? Our pi bond can attack. We do have the ability for the electrons to leave. Then the lone pair could attack, and we'd satisfy that cyclic tri-system. We don't have that. Okay, where does that system appear? That system appears in the previous question. Okay. That appears in this previous system. If we look at the best Lewis structure for that, that's the Lewis structure that we've got. That's not the one I drew before, was it? Okay, why not? We can shift the electrons in, shift the electrons onto the carbon. That carbon has both a lone pair and kind of a pi bond-ish system. In this case, the leaving group is nitrogen, and it entirely leaves the structure. Okay? But it's the same kind of concept. How do those electrons bounce around? We would typically not say this second arrow here makes sense, okay, because nitrogen's more electronegative than carbon. Why are the electrons moving towards the carbon, though?
Because otherwise we would see octet.
Because the other nitrogen is forcing the electrons in. Okay? So we have to look at a structural effect all the way out to see how those things could be manipulated. Okay? So if we go back to our oxygen structure, do I have lone pair electrons there? Yes. Do I have a weak bond? Okay. I could shuttle the electrons to that oxygen, right? Okay. That's reasonable. That is a possibility. Okay. I'd be ejecting what, though, as a leaving group? Hydroxide, which is a bad leaving group. Okay? Hydroxide ultimately isn't a bad leaving group as long as it's leaving into a basic system. What was the name of this functional group? It's a harder one. What'd you say? This is a peroxy, okay? Peroxy acid. This is an acidic functional group. Hydroxide's not going to be a good living group because it's leaving into an acidic environment. Strong base, acidic environments, those clash, that doesn't work. So while that is a potential option, I can't react that oxygen in that fashion. Okay? Could I have the electrons go the other direction? Okay? The result being oxygen, whoops, and now a lone, well, that's an eraser. A lone pair there. Looks kind of weird. Isn't there resonance? No, because exceed the octet on the oxygen. Okay, so there's no resonance for that. We'd be looking at having just a lone pair chilling on what atom? Carbon. Is carbon able to stabilize electrons? No, because
It's small.
small and low electronegativity. The hydroxide couldn't stabilize the electrons. The carbon certainly isn't. Okay? So while that oxygen had lone pairs, that was a decent place to attack, okay, or to see if it satisfies our conditions, but unfortunately it doesn't work. So let's take a look at the last oxygen. So there's a pair of electrons. Could this bond break? Okay. Oh, you're even making a face at me. Let's draw it out. Oh, we'd have a negative oxygen. We can't possibly have that negative oxygen, could we? That would be horrible. It's not as if there was like resonance to say stabilize it. Oh, there is resonance to stabilize it, which means that's a good leaving group. We now have an atom that lasts oxygen with a pair of electrons and a good stable leaving group, which means we have a reagent that's going to satisfy the conditions for that cyclic tri-intermediate. Okay? That reagent is commonly known as MPCBA. Depending on the mood of whoever's writing the test question, sometimes you'll see it written as MPCBA. I dislike that because that's a shorthand of the actual name. Okay, so that's difficult to trace it down. What I would prefer is them actually drawing the structure. Okay, sometimes they do that, sometimes they don't. Okay, that structure can get represented in a few different ways. Okay, largely stemming from that being an R group. Do I care what that R group is? No. All of the chemistry is on that oxygen, and the rest of this being resonance. So I don't care what that R group is. That could be an elephant for all I care. The chemistry is still the same. It's still going to do the same cyclic intermediate process. Okay, kind of makes sense? So don't get tripped up in saying, well, I don't know what that R is. It doesn't matter. As long as you have that basic functionality, which is a peroxy acid. Okay? That's going to fit the pattern of your cyclic intermediates. Okay? The last one on the list is our mercury, which we talked about already. Our OAC. Notice that I've shown it as an OAC and I broke it down structurally so we can see it. We've got the lone pair on the mercury, which again is typically implied. It is very rare for anybody to actually show it being present. It is present. Okay? Do we have a weak bond where the electrons could break off? Could that oxygen stabilize those electrons? Yes, for the exact same reason that the peroxy could stabilize the electrons. It's effectively the same leaving group. Okay? So if we can recognize those patterns, we can recognize reagents that are going to fit into this category, and that can help us predict what those structures might be at the end. Kind of, sort of? Yes?
Using mercury, it's 2+, and that's why that's ionic mercury?
Yes.
Okay. What's the charge on that one?
It's 2+.
Okay. has 6 electrons?
Don't bring in Lewis structure.
Okay. Got it.
Okay. The next part in our cyclic structures, or cyclic 3-membered structures, is does the reaction continue? Do I need that second step? That's where that question mark is. Okay? And as we addressed, that question mark has to do with that intermediate structure, or potentially intermediate structure. Why would I continue to react?
It's not stable.
Why is it not stable? I see that charge. If there's a charge there, I should continue to react. If there's not a charge there, don't react. Okay? Leave it as is. Okay? So if we go through and take a look, okay, in that first box, we look at that cyclic intermediate. Do we have charge on our cyclic structure? No, which means it's stable. You're done. It does not continue to react. How about the second box? Okay. There is charge, which means
It's not stable.
it's not stable, so it'll continue to react. Last one,
Stable.
no charge, meaning
Stable.
stable. Okay. Thankfully, somebody made a face about it. That's cool. We got the last box. If you're unsure, what should you do? Continue to react and be like, did that make it better or worse? If it made it worse, you shouldn't have done it. Okay? So what do we mean continue to react? Look at the pieces that you've got access to and see what happens. Okay? If I want this to continue to react, I'm saying that carbon needs to somehow break off. Okay? It would need to steal electrons. Since it can only steal electrons from a single bond, I'd be breaking electrons from one of those bonds. Okay? So we could do that, which would then mean what happens to this carbon, our purple carbon.
It's not positive.
It's now positive, so what would need to happen?
Electrons.
Electrons from the nitrogen would need to come in. What would the result be of that arrow pushing?
Nitrogen would have a charge.
We'd have a positive nitrogen and
Negative carbon.
a negative carbon. Did I make this more stable or less stable?
Less.
Less stable. Should I have continued?
No.
Nope. Leave it where it was. Okay? So we can use some ideas about stability. That first stability argument we're going to stick with is the charge. Okay? If it is uncharged, it's stable. Don't do anything to it. Okay? Leave it alone. If it's unstable, then yes, continue. Okay? In that continuation, what needs to happen? So let's look at the middle box because that's one that continued. What makes that intermediate unstable?
It's charged.
Okay, what's charged?
Positive.
A positive bromine. So what does the bromine need to do? Gain electrons. So we'll have to steal electrons from within. We can't steal electrons from the outside because
Octet.
we would exceed the octet, okay, which in and of itself isn't a big deal, but we'd have to break those electrons down, meaning we'd be putting a negative charge on carbon. Can carbon stabilize that negative charge? Nope, which means that big curved arrow was a bad idea. We got to get the electrons from within the structure. What happens to our carbon?
It's positive.
Becomes positive. What do I need to stabilize it?
Electron.
Electrons from
The other one.
the other bromine. What's the end result?
It's open.
The original bromine that was positive is now neutral because it's now gained electrons. The bromine that was negative is now neutral because it's now shared electrons. Is that result more stable? Yep, we should have done it. Okay, you should be continuing that reaction. Kind of makes sense? Okay, so again, we're trying to come up with those classifications that allow us to be able to make these larger predictions. It is not easy. Okay? But what we're attempting to do is to simplify the amount of memorization we've got to do. Okay? So, your turn. Practice with the cyclic tri-electrophiles. Predict your product. Is there a nucleophile present? Where is it? Okay? And then that's not is as, but is a second reaction step necessary? Okay, so what you may find is that a second reaction is necessary. If it is necessary or you think it's necessary, what reagents might you need to add? Okay. You should have been spending some time reviewing with these reagents, so hopefully you already have an idea on what needs to be happening. Try and come up with some predictions. If you got, so we'll go through a couple big hints. Number one, this is on the cyclotri electrophiles. You need to be somehow forming, if you're thinking about a mechanism, you need to be forming that cyclic intermediate. If you aren't forming a 3-membered cyclic intermediate in any of these, something is wrong. Okay? These are on this slide for a reason. All of these form that. Okay? If we go through and look at a breakdown, we attack, we have the leaving group leave, we have the electrons come back. Okay? The result, bromine, bond, positive, Br minus. Okay? Do we have chiral atoms in that structure? Yes, because we have chiral atoms, what do we need to worry about? Stereochemistry. Okay. For me personally, I think it's easier just to draw wedges, so I would draw them both as wedges. The next bromide comes in from the back side. And sorry, I just lost track of what my structure was. Okay, and that bond breaks out. Okay. So could that intermediate have formed where they were dashed? Yes. Which means, is there another product?
Yes.
Yes. And I would have to draw that other product. Okay? So I end up with 2 products in this case. So the question that could be asked is, which of the following is the product to this reaction? Okay? 1, 2, 3, or D, 1 and 2. Okay? Or it could just be which of the following is a product, and you get 4 distinct structures, okay, that have slightly different variations off of them. Yes?
If you attack the other carbon with a nucleophilic, you end up getting like.
If you go through and do it, you'll find that it's exactly the same because we can't tell a difference between those 2 bromines. If we change the reagent where the nucleophile was no longer bromide, it was now water, this problem explodes into a whole lot more possible products.
I mean, it doesn't have to always attack at C3. It can attack at C4, correct?
It would be C2 or C3.
Once you add, okay, yeah. But
And
from
then,
the original.
yes, that negative bromide could have attacked either of those 2 positions.
Okay. And then
Because
just
there is no difference
if you
between
make
them
the opposite way,
currently.
it comes up, okay.
Yeah. Okay. If we move down to the next one underneath it, okay, again, we should be focusing on a cyclic intermediate. Where's that cyclic intermediate in this case? It's with that mercury. So what do we end up with? There's our mercury. We could go through and show our wedges because, again, we have chiral atoms. Okay, we could also throw in the OAC if we really wanted to. It's ultimately not that big of a deal. So what's the nucleophile? Because that mercury is now going to come in as being positive. It will have lost electrons and gained electrons. It still comes out as a kind of a positive structure.
Does it?
Ish.
I thought it lost.
Ish. Just accept it.
Okay.
What's our nucleophile?
Water.
Water.
It's really weak.
Good statement. The water is really weak. Are both of those positions where the mercury is connected the same? No. In the case with the bromine, they were both secondaries. There wasn't really a difference between them. We now have an added complication because those 2 positions are different from each other. So now the question becomes is where does the nucleophile attack? Does it attack 1 or 2? Okay. If we say 1, what is the argument we're saying? What kind of reaction would we be running if it attacks position 1? What What is the relationship between position 1 and position 2? And conveniently, the numbering of 1 and 2 is really important or really helpful. Primary versus secondary. If our nucleophile attacks position 1, what kind of mechanism are we running? This is a nucleophilic attack with a leaving group. We're doing the substitution. We'd be saying we're doing what kind of substitution? An SN2, least sterically hindered. Okay? In an SN2 mechanism, what does your nucleophile need to be? Is that strong? Should it run SN2? No. How should it run? SN1. Because it's running under SN1, because I have a weak nucleophile, where does it need to attack? The more substituted position.
Are we going to form another intermediate?
The end result of this would then be our OH2, the positive charge, and here's our mercury chilling out over here with our OAC. Yes?
You used HGOAC2, and you only got HGOAC on there.
What happens when our nucleophile attacks?
You have a leaving group.
You kick off the leaving group, which means no more OAC. I've ejected one of them. That's why there's only one OAC. I've lost one of them.
Yeah, no, I know that, but doesn't that make the...
If you're going to go back to charge, I'm going to tell you right now, stop. I told you to stop. Don't worry about the charge. We're pushing the mechanics behind this for a reason in this way. Okay? We need to push further, not slow down, unfortunately. Okay? So, the mercury chills out of here. We have a positive oxygen. Does oxygen want to be positive?
No.
No. So what needs to happen?
One of the hydrogen, it has to be protein.
Whoop. We lose the hydrogen. And we'd have that as a product. How many people like mercury stuck to an organic compound? No, that looks awful. So are we going to need another step? Yeah. Are we given another step? No. So at this point, we're stuck. Turns out with the mercury reagent, we do have to cleave that mercury off. What do we cleave it off with? For those people that have read ahead in the textbook, we would do a second step, and that second step is to add. Okay, I'm glad we're reading ahead in the textbook. That's always a good sign. Sodium borohydride. What makes that species reactive? Not to be subtle with the hints.
Hydrogen.
Hydrogen. What charge is that hydrogen?
Negative.
That's a negative hydrogen. Why is that hydrogen negative?
You said hydride.
So one option is listening very carefully to the words that are coming out of my mouth, which is sometimes a good idea. Right? We would have a negative boron. Does boron want to be negative? No, and in fact, boron only wants how many electrons? 6. Boron's octet is 6 electrons. How is it exceeding its octet? It's not hydrogen ion, it's hydride. We have a hydride that is stuck and being temporarily stabilized by that boron. That negative hydrogen is now being used to do what? Attack the carbon and eject the mercury. Okay? So what we end up with this reagent is the addition of H and OH across the pi bond. Okay? So that second reaction all the way through to an ending is just this. Okay? Have we added H and OH to a pi bond already? Yes. Yes, you did. Cool. How did we add H and OH before?
Acid base.
You just added acid in the presence of water. Okay? Chapter 11. Okay? That acid activates the alkene, okay, so that we have a carbocation. Water can then attack, and we get the exact same product as here. Why would I use mercury and a hydride reagent instead of just adding acid and water? much harder question, and it all has to do with the intermediates generated. In the acid and water, what do I generate?
Carbocation.
A carbocation. And what do carbocations do?
Go to the most substituted position.
They will rearrange. Anybody see any carbocations?
No.
No. If I use mercury, what happens to the amount of rearrangements?
It doesn't.
It doesn't rearrange. The mercury reagent will add the exact same thing, H and OH, but it adds it in such a way that I don't get rearrangements. That is a really important distinction. It is one that is very commonly tested on, because students will sometimes pick up the patterns of H being positive and oxygen being negative, and that's what an alkene is, positive and negative. Oh, if I add acid, H plus, and water, I get those pieces. You do. But if your structure is aligned in such a way where you could do a rearrangement, you're now dead in the water, that answer becomes invalid because the rearrangement shifts where your pieces go. Okay? That's how they test for mechanism understanding. Okay? Do you understand how the reaction worked? Because it limits secondary complications. If you don't understand the mechanism, how would you know? You had to memorize it. This is why people get bogged down and go, oh, I have to memorize so much. Because you aren't getting the time to practice and deal with how those things work. Okay? So let's clear all that. Upper right hand, what's going on with that? What's the most reactive thing? So the pi bond's a good suggestion. How would the pi bond react? By providing electrons, so it's either a nucleophile or a base. I'm going to argue that that was actually the wrong answer to my question. What's the most reactive thing present? Sodium hydroxide. Why is sodium hydroxide more reactive than my pi bond? Because sodium hydroxide is a strong base. It's part of its identity. Okay? We're looking at hydroxide with a formal negative charge in comparison to just a pi bond. Okay? So that hydroxide's the most reactive thing there. Why does that become a problem with the alkene? How does the alkene react, that pi bond? As a hint, you literally told me what the answer was like 2 seconds ago. How does the pi bond react? As an extra hint, it's actually written on the slides. It's a nucleophile or a base. Why is that a problem when looking at hydroxide? Because it's also a nucleophile and a base. Okay? Which means don't react the hydroxide with the nucleophile base. So what does the hydroxide need to be reacted with? I'm going to have to look at the top structure. When I go up and look at that top structure, how is it most likely to react? Okay. Why the H? What'd you say?
Base that is AC.
Is that carbon also not positive? So yes, we could say proton transfer, and I'm not disagreeing with you. All I'm asking is, isn't the carbon also positive?
Yes.
Yes. What should the base react, or the hydroxide react with? Should it react with that hydrogen or with the carbon?
The carbon?
Okay, to react with the carbon, what must it get by?
Chlorine.
A bunch of chlorines. Okay, or get by the hydrogen. And what's the problem with getting by the hydrogen? The hydrogen's literally the other part that's reactive. Okay? Which means, what's the base likely to do, or a hydroxide likely to do? React with the hydrogen, which means the electrons get shuttled to the carbon. And now we've got a whole nother issue, because when we look at that structure, we now have a negative carbon. And how should a negative carbon react? Like a nucleophile or base. I'm still dead in the water with it still being a negatively charged thing. But what else is special about that carbon? It has 3 chlorines. And what is special about a chlorine, in particular a chloride? They are electronegative, and they are large, making them good leaving groups. And we would end up with that structure. And with that structure, you should be freaking out a little bit. Why?
You didn't write a formal charge?
I didn't write a formal charge. Tell me what that formal charge is.
Small one.
Try again. There is no formal charge.
There's no formal charge.
It's not have its octet,
Okay.
so it's
It does not have its octet,
It's positive.
which means, what could it do?
Act as an electrophile.
It could act as an electrophile by accepting electrons from our pi bond. But it also has a lone pair of electrons, which means
It can act as a nucleophile.
sorry, he or she is probably not going to help you now.
Hmm?
Don't worry. And we've now formed our cyclic structure, which is screaming at you at the top of the slide. We need to be forming that cyclic structure. If you aren't forming it in any of these reactions, something went wrong. And we end up with that structure. What's the problem with that drawing? Or what's a complication with this drawing? Those are chiral carbons, which means I need to be specifying wedges and dashes. Okay? Because your instructor defaults more easily to the wedges, we could go through and draw on the wedges. Okay? What would the other structure be? Where those are dashes, which would be and an enantiomer. Does everybody want to agree with that statement? No, you're vehemently saying no. Why?
The chiral.
You also have another chiral atom. So the question that could get asked, what is the relationship between the products of this reaction? Enantiomers, diastereomers, identical, meso. You now have to tie in what is the chemistry of the reaction and be able to pull chapter 6 in to identify those relationships. If you remember just that additions tend to reform enantiomers, now you're answering the wrong answer. This is why we have to be careful in what we memorize. Okay? We have to think about those pieces. Addition reactions will produce 2 different alignments, or 2 different, it's the best way to think about it. It's 2 different alignments. The relationship between those 2 alignments is oftentimes enantiomers, but not always. Okay? They can also be diastereomers. Yes?
When we write out a chiral atom, if you get like the product, can you just do not the wedges and dashes and maybe understood that?
No. So I believe what your question is could I have just written it, I think how I initially had it. Like that?
Yes.
No. All right. That is not to say that they couldn't just draw that as a possible answer. Okay? They probably wouldn't because there's already a chiral atom there. Okay? And what they're probably pushing for is a diastereomer reaction. Could they draw it like that? Yeah, that's a possible explanation. And in that case, what they're trying to do is just say, do you understand what those reagents do? Okay? It goes through this weird cyclic structure where it generates this. And now what we're saying is we're making it easier. We're saying, I don't care that you know it produces both wedges and dashes. Do you understand that that's the basic structure that comes out of it? Okay, so I can draw that. It's not technically correct, but it's the level of the question that's being asked.
I was thinking of something where it was, something like an implied.
There's no implied wedges and dashes. You can't get away with that.
Okay.
It's either you're just showing it because you're trying to say the basic connectivity, in which case that's the question that's being asked, or you're not showing it at all and you're being asked for it, you're now wrong. Okay? This purple structure gets a special name. Why might it get a special name?
Because it reacts specially.
It reacts kind of weirdly, right? Okay, that special name gets known as a carbene. It should look kind of familiar to you because it was on exam 1. Go back and take a look. I asked you to assign formal charge for that carbon on exam 1. Okay. The last one, the lower right-hand corner. Okay. Again, really not a fan of it getting phrased this way, but it is super common to see it just phrased out. What is the product of this reaction? And then showing MPCBA like that. Okay. MPCBA is our, in fact, because I don't think I have the mechanism drawn neatly somewhere else, we'll just do it here because it's a neat mechanism. So everybody see the peroxy? Okay. This is now metachloroperoxybenzoic acid. The metachloro is in reference to where the chlorine is located on that ring. The peroxy is our oxygen-oxygen benzoic acid because we have a benzene with a carboxylic acid-esque functional group. Okay, so that's where the name is coming from. How does this reaction work? Well, again, we've already targeted that oxygen has both a lone pair of electrons, okay, and has a good leaving group. So those electrons can shuttle out as a good leaving group. If the electrons shuttle up like that, what happens to this carbon? It would exceed its octet. It currently has 4 pairs of electrons around it. We're adding another pair in, which would mean we exceed the octet. So what do? We break the pi bond. That oxygen up at the top would now have a negative charge, which in and of itself isn't a big deal because of resonance and stabilization and all of that. But I wonder if there happens to be something floating around nearby that happens to be somewhat positive. Like that hydrogen. That hydrogen has now exceeded its octet, so what happens? The mechanism for your MPCBA, your epoxide formation, 1, 2, 3, 4, 5 arrows, all at the exact same instant. It's kind of a neat one. If we draw out the end result, okay, we've now formed the bond to that blue oxygen with the cyclic. If we go through and look at the other piece, I think I drew it this way. Okay, and we would get those 2 pieces. Let's take a look at that product real quickly. Do we have a stereo center?
Yes.
Yes, we do. So we would need to go through and specify it. Okay, what would the relationship be between the 2 products formed? Okay, enantiomers. How do we know they're enantiomers and not say meso? You're like, meso? Why the hell would meso matter? If this was, whoops. If this was our starting material, guess how many products we get? We get 1. Because it's a meso compound. What is the difference between this starting material and the one given in the question? Cis versus trans. Because this mechanism all happens at the exact same instant, what happens to the relationship between those 2 methyl groups, the substituents? They stay the same. Okay? So we have to be aware of that when dealing with these cyclic tri structures, is that orientation is permanently locked into place. Okay? So, 4-membered transition intermediates. Okay, in this subclass, we've got a small leaving group. If we take a look at the first one, we've already seen that one, so we should know. Okay, if the bromine attacks and I kick out bromide, is bromide small? No, so that doesn't fit. Okay, that's not going to be in our small leaving group category. How about in the next one? If electrons come in and attack that hydrogen, these electrons shuttle out. That would be hydride, right? Is hydride a stable leaving group? No, that's a horrible leaving group. This reagent, H2, fits in this 4+ transition state intermediate. Okay, that's part of it. Okay, last one gets all sorts of goofy and weird. Okay, I didn't say it was perfect, but this is the best I got. What's the thing getting attacked? Oxygen. What's the leaving group? This fits back to that pattern. Our leaving group in this case is just a pair of electrons going to the osmium. Is a pair of electrons large? No, so what happens? This is going to be fitting our 4+ member transition state as well. The electrons come out, we shuttle the electrons to the osmium. Osmium is like, holy crap, I've got too many electrons. So what does it do? It shuttles more electrons out. Meaning in our intermediate, what do we have? We have the 2 carbons here. One is connected to an oxygen. That oxygen is connected to osmium. That osmium is connected to this oxygen. And that pi bond that we just broke is now making a new sigma bond between the oxygen and this carbon. And we end up with how many atoms in our cyclic structure? We end up with 5. 1, 2, 3, 4, 5. Okay? So with the hydrogen, we've got that 4. With the osmium structure, we have 5. Okay? The osmium structure is a giant flip and stretch. Okay? What we're trying to do is force something onto a non-natural state to explain those arrangements. Okay? So I fully admit that that is a weak comparison for this, but it at least establishes some of those dynamics where we can see those pieces and how they can potentially align. Okay? So if we see other things that fit this category, okay, 4+ transition members, we know we've got this kind of system going on. Okay? So, in this case, BH3. Okay? So if we ignore the bottom structure, what happens now? Right? Boron has how many electrons around it? 6. How many electrons should or can fit around an atom? Particularly boron. 8, which means it has a hole. A hole for what? Electrons. Electrons coming from where? From the alkene. There's the pi electrons coming up. Boron's not happy with those extra electrons. So what does it do? It ejects the hydride. Is hydride a good leaving group? No, because it is a horribly unstable leaving group, it can't just float off into nothingness. It has to be stabilized, and it has to be stabilized immediately. If we look back at the carbon structure, we'll call them blue and purple. If we go through and say the boron forms to the purple, what is forming on the blue? What charge would build?
Positive.
A positive charge. What charge just built on the hydrogen?
Positive.
On the hydrogen?
Negative.
A negative. So what happens? The electrons immediately come back out, and we end up exchanging the location of where the sigma bond is. Okay? The result, I don't know why I cramped it so much, is you'll sometimes see this kind of dotted line system where we're taking the electrons from the pi bond to make a sigma bond between our carbon and our boron, and we're taking the sigma bond from the hydrogen and the boron, and connect it to our carbon. The end result is that we've formed this structure. Okay? We've now added hydrogen and boron across the pi bond. Okay? The same general principle is happening with our osmium structure. Right? The electrons from our pi system come out to share with the oxygen. We exceed the oxygen's octet, so the electrons shuttle back to the osmium. Okay? Osmium now has more electrons than it wants, so it breaks the pi bond to the other oxygen, shuttles them back out. The end result is that we've got a 5-centered intermediate where all the electrons are changing. The end result for the osmium one, though, is we end with a formal 5-membered ring. For the boron and the hydrogen, we don't have a 4-membered ring. Why not? What do you got, David?
You can have 2 bonds.
We're making and breaking, in this case, we're breaking all sigma bonds. And the metal with the osmium, what are we breaking? Pi bonds, which means I'll have leftover sigmas. Those sigmas are keeping my final structure together. Okay? So it's a question of which bonds are breaking through that cycle. Okay? Oh, so our leaving group in BH3 was our hydride. Okay? This goes back to looking at the chemistry of our boron structure. It has an empty p orbital. The electrons can get dumped in. Electrons in that sigma bond go to the hydrogen. But that would suggest that hydrogen is more electronegative than boron. It is. We're used to saying hydrogen has the lowest electronegativity. It's actually more electronegative than boron. The bond does appropriately break according to electronegativity rules. Who knew? It's kind of neat. Okay? And that helps to explain what's going on with that reagent. Okay? So our boron is kind of neat because of that. Okay? What happens if we switch this up as a potential example? Let's take a look at 2Z butene. What would Z mean? On the same side, so it might help if I actually drew that right. So there's 4 carbons. At the 2 position, we have the pi bond. If we react this with our boron reagent, what do we end up with? We'll have our hydrogen, and we'll have our BH2. The electrons come out, react, electrons come down, react. That hydrogen and the boron were added how to the pi bond? I like where you're going. Yeah, same side. So if we were going to reference this addition reaction, because this is strictly an addition, this would be a syn addition. Right? There's our adverb again. We're describing how those pieces are added. So if you go through and look at tables of how things react, that's exactly how they reference the boron reaction as a syn addition. Okay? Why does it have to react as a syn addition? Well, you tell me. Is hydride a good leaving group? No, which means it has to react on the exact same side. Okay? So depending at where you're looking at each of these individual reactions, you will hear references to syn addition, anti-addition, all that kind of fun stuff. Okay? You have to be aware of those dynamics. The boron one is one of the reactions that is super tested on because the stereochemistry is super clean. Okay? How many times have you seen boron attached to a structure?
I haven't.
You haven't, which means is that a good thing to be stuck on the structure? No, so what do? We react it some more to get rid of that boron. Okay? How does the boron react? How does the boron react?
As an electrophile.
As an electrophile, which means that next step, what are we going to add?
A nucleophile.
A giant source of electrons. That giant source of electrons ends up being, stupid thing, peroxide. What does peroxide give you?
4 lone pairs.
More lone pairs. Why are those lone pairs important?
Because that's what you need in order to connect.
All right, let's kind of push this structure around a little bit, put those hydrogens up there. This is, by the way, the wrong mechanism. We'll see the formal mechanism here in a second. I need those lone pairs to go into the boron, right? Okay. If that oxygen gives up its electrons to the boron, though, what charge would it become? Positive. Does oxygen want to be positive? No. So what is it going to do? It's going to find electrons. Where are the closest electrons to it? We could go into the hydrogen, or I would argue there's an even weaker bond there. The oxygen-oxygen bond is an exceptionally polar bond. We've got two very electronegative elements pulling at each other. It can steal those electrons, and it can shuttle the electrons in. That's two arrows that we could get away with showing as, whoops, 1. Electrons go in. What would happen then to our blue oxygen? It would not have a full octet. Okay, so that's not good. What happens to the boron now that it's accepted electrons from that first oxygen?
It doesn't need those 2 electrons, those electrons in the bond.
It's exceeded its happy octet, right? So it needs to eject something. What does it eject? The bond between the boron and the carbon. Where do those electrons then go? They could just go to the carbon, building what charge on the carbon? A negative. What happened to our blue oxygen? Became positive. Oxygen doesn't want to be positive. What does it need? Electrons. What happens to be right next door to it? A carbon source with electrons. So what happens? Does that mechanism look kind of similar to the mechanism we just drew for the alkene? Yeah. It's pretty much the exact same thing, except instead of reacting a pi bond, what are we reacting? We're reacting the peroxy sigma bond. Okay? What makes this really important for this dynamic is that this is all happening at the exact same instant. So if I showed this bond to the bromine being wedged, where's that oxygen bond going to end up? Can it get behind the structure? Where are the electrons coming from? They're coming from a wedged bond. So that from that wedged bond, they're all of a sudden going to snap and go the other direction? No. What happens? We maintain stereochemistry. Whoa. Okay? That's pretty freaking crazy. Okay? And the reason we're able to do that is because of boron's empty p orbital to facilitate that electron motion. There's no way you'd be able to get that oxygen. Remember, you're looking at a square now, okay, where we're somehow breaking it around on the other side. It's not going to form that nice tight square. Because we're constricted by that cyclic tri structure or tetra structure, we maintain the stereochemistry in our end product. Very commonly tested on. Okay? So if we push this out, we'll almost push out in a second. So if you go through and review the reagents in these, ones that need a second reaction, the boron reaction needs a second one because what did we put on the structure? Hydrogen and boron. Do we like boron on a structure? No, that looks weird. So let's get rid of it. What do we like on structures? Oxygen. Why? Because why not? Okay, so we follow it up with the addition of oxygen. So if we look at the boron reagent, what did it add? H and OH. If we look at the mercury reagent, what did it add? H, and really the mercury reagent did it a little bit differently. The mercury reagent did OH, then H. Okay. Wasn't there another reagent that added H and OH? Like, didn't you ask this question? Yeah, I think if I rewind back about 20 minutes in the video, you'll hear me ask the exact same question. And there was a long pause then, too.
Acid base.
Adding acid in the presence of water adds H and OH. There are 3 different ways to add H and OH to a pi bond. Why do I need 3 different ways? They all do it differently.
So if you're looking for a particular alcohol, I don't want.
So if you're looking at a reaction where they asked you to predict what reagent is used, a very common reaction is an addition reaction where you've added H and OH across a pi bond. Guess which 3 answers show up? Boron, mercury, and an acid in the presence of water. Okay? You have to be able to discern which one does which thing. What's the issue with the acid and water?
You're going to get probably the least substituted alcohol.
No. We haven't even brought that into it, believe it or not. Rearrangements. Okay? Acid and water, you've got a complication of rearrangements. The mercury and water, do we have rearrangements? No. The boron and water, did we have rearrangements? No, the boron and water is actually even faster and more compacted. Everything happened. Each step happened at its own individual time. Okay? So what's the deal between mercury versus boron? Why are they different? The H that was added in mercury was added as what charge? Shice. I didn't want that one. It's going to reference the first step.
H minus.
Okay. When we go through and look at each of these, I always forget that it doesn't work out quite as cleanly as that. The H being added is being added as H minus in both cases. Okay. The important clutch on this is deciding when and how the OH was added. Okay. The OH gets added in this first case to the more substituted position. Okay? Because it's ejecting the leaving group. When's the OH added in the boron reagent? It's adding to replace the boron. What charge was the boron when it was added? How did the boron react? As an electrophile. So the boron was added to the least substituted position, which means the OH in the case of the boron reagent was added to the least substituted position, which means the H was added to the most substituted. And the H over here was added to the most substituted. Least substituted. H plus in water, this goes to the least substituted. I wonder if somebody made some moronic observation about this.
Did the guy get a name?
Yeah, he got a name for it. I butchered the hell out of that. Oh, maybe I got it.
No, you got it.
Markovnikov says the hydrogen goes to the least substituted position. So if we look at the acid and water, it's a Markovnikov addition. If we look at the mercury reagent, it's a Markovnikov addition. If we look at the boron reagent, it's not Markovnikov. You will hear anti-Markovnikov referenced. Laura, the queen of our tutoring center, made a very good observation about calling it anti-Markovnikov. What is the issue with calling it anti-Markovnikov?
It would make it sound like it was the most substituted.
Is anti used in other contexts?
Oh, yeah, it's an anti, like opposite.
Anti is an opposite. Anti is an anti-addition. Anti has a multitude of other references. When we call it anti-Markovnikov, really what are we saying?
It's just not nice.
It's not Markovnikov. So when you look things up online and they're referencing anti-Markovnikov, the anti they're using is not our organic chemistry context of anti. They're using the English context of anti, which is not. Okay? So be careful when using secondary videos as referencing, particularly around Markovnikov, because you'll hear Markovnikov addition and anti-Markovnikov addition. Anti-Markovnikov addition just means not Markovnikov. Okay? It has nothing to do with the alignment of where the groups are. Okay? That would also be added as a anti-addition. Okay? So to just add confusion to that, let's just make sure we're aware of this. You could have a reaction that is anti-addition and anti-Markovnikov. Or you could have a syn addition that is anti-Markovnikov. What? Yeah. That's why you should use non or not Markovnikov to remove that ambiguity. Okay? So, in most cases, the details of those mechanisms are not necessary. Okay? So we don't have to memorize the mechanism. What we do have to do is memorize the repercussions of them. The repercussions I gave you when we went through and addressed the hand-wavy mechanisms. Okay? If we go through and look at the Mercury workup, okay, we did that with our hydride. If we go through, yeah, we did that. So if we look at our end result, our Mercury reagent adds the H and OH in a standard location. The H goes to the more substituted position. Why? Because the H is replacing the Mercury. The OH goes to the least substituted. Why? Because the OH is breaking open that three-membered ring. Okay? Why is it attacking the most substituted? What can you tell me about water as a nucleophile? It's weak, and weak nucleophiles suggest which mechanism? SN1, and SN1 suggests which substrate? It suggests the more substituted substrate attack. Okay? That's all of these pieces that are interconnected all the way through it. Okay? We've got that hand-wavy mechanism we've got there. Kind of just want to work through these examples. So if we look at this, for that first one, okay, we've got a pi bond. If you just memorize that when you have H and OH, the boron, that you add H and OH, there you go. Do we need to worry about any stereochemistry with that?
No.
No, why not?
Because there's no chiral centers.
There's no chiral atoms, so I don't care. Okay? What if... never mind. How about the next one?
You add H and OH.
I add H and OH. Oh, wait a second. Doesn't this one get a little bit more complicated? Are the carbons there the same?
No.
No, they're different. So I could add H and OH in this fashion, or I could add H and OH in this fashion. Well, dang, which one is it? Do I get both?
No.
No. And this comes back to how that reagent works. The first step adds the hydrogen. The hydrogen is getting added as what charge in the first step? It's getting added as H minus. Which of my carbons is more positive? The tertiary one. We know that because of, could say substitution, resonance, be a more stable carbocation, which means where should my negative hydrogen go? To the tertiary position, not the blue one. Okay? So if I understand something about the reactivity of those pieces and when they get added, I can predict that chemistry. Yes? The relationship between the red and blue is known as regiochemistry. Where did the atoms add to the structure? Okay? This reagent is regiospecific. It only adds the H to the more substituted here, and it adds the OH to the least substituted. The next part that we would have to be concerned about are those stereocenters. Yes, which means this is not going to be a valid answer. To get the valid answer, I would have to know the arrangement of those. Okay? Are they added in such a way? I know I always favor wedges, but whatever. Are they added in such a way where they are on the same side, or they added where they are on opposite sides. What did we say about the boron reaction? Syn addition. Syn addition means same side, which is my valid answer. The red one. The green one is invalid. They're added on opposite sides. The boron reagent all the way through adds it on the same side, which means the OH that I've added and the H that I've added must be on the same side. Do they have to be dashed? No, they could have been wedged. I get two products. The relationship between those two products is enantiomers in this case, okay, because there was no other stereocenter messing with it. Okay. How do we show that? We could show that with wedges and dashes. I wonder if there was another way that we could represent a cyclic structure like that. What have I just drawn? This is a Hayworth projection. Okay. We've taken that flat structure and turned it on its side. The CH3 is aiming up, the OH is aiming down. We've got ups and downs to reference those. You can see them drawn as Hayworths as well as you can wedges and dashes. Okay. The far right and top, and I know we're out of time, we add H in the first step. Okay. This first step gives me H. Where does it place the H? The most substituted position. So there goes my H. The next step adds the OH, which goes to the least substituted position. That's really weird, because if I had an acid and water, what happens? I get the opposite. How would I know that? Mechanisms. You have to align those charges. Okay. The extra last one becomes extra fun because it's an alkyne. Mother, really? Okay. Officially, it doesn't run with these exact same reagents. We have to add some other reagents to this, but it's ultimately the same characteristics. Okay. Our chemistry is ultimately the boron and the hydrogen. I don't care that there's 3 hydrogens. I care that I have 1. I can make the other 2 things whatever the hell I want. It's still going to act roughly the same way. What is that same way? It's going to add H and OH. The first step adds H is what charge? Negative, which means it goes where? The more substituted position. The next step adds the OH, and because I already specified where the H goes, the OH must go to the other position. There's a second pi bond, so this could react again, except hold up and wait. Is there really just a second pi bond?
Well, you can do resonance. You can't put it on the...
Yes, there's a pi bond there known as a alkene. But is that all that's present? There's also the alcohol. Those 2 functional groups are overlapping, which means we have a new functional group. We have the enol, which means I don't just do another addition. This goes through the keto-enol tautomerization to end with the carbonyl. More appropriately, in this case, the aldehyde. Okay, in this case, yes, butylaldehyde. Okay. Also very commonly tested on that keto-enol tautomerization through the triple bond. Okay. Does it have to be the boron reagent? No, it could have been acid and water. It could have been the mercury reagent. They'll all ultimately do the same thing. They react once to form the enol. The enol tautomerizes to the carbonyl. It trips people up because you don't recognize the keto-enol tautomerization. Go frickin' figure, because the keto-enol tautomerization is something we talk about in second semester primarily. Okay? We just don't address it to its full extent in first semester. Okay? It will absolutely show up. You got to watch out for it. I can't make that statement. It may not absolutely show up. Unfortunately, we're done. If you got questions, you can ask.